Okay. What I'd like you to do is go into the applications and get out the Ch09 app demo. And it should look like this and open up to problem 1, demo 1. And if you can just let me know when you're ready.
I have it up.
Okay. I'm going to begin reading the problem while you're pulling that up and working through it, Tiana. A researcher wants to test whether 3 different study break strategies influence students' test performance. She randomly assigns students to one of 3 conditions before giving them a test of problem-solving skills. The 3 conditions and scores are listed below. You can see them here. Group 1 were assigned to have a 10-minute social media break. Group 2 were assigned to have a 10-minute walk outside. And group 3 were assigned to have a 10-minute quiet rest. Here's your study right there, right, Cassandra? Sort of. Okay, she hypothesized that students taking the social media break would perform worse than those who walked outside or those who rested quietly. Conduct an ANOVA to test her hypothesis using alpha 0.05, then conduct planned contrasts in accordance with her hypothesis. So this is a slightly shorter version of a problem because you're already given these calculations right here. We're also noticing that our n's are unequal. We have n equals 9 here, n equals 11 here, and n equals 10 here. So there will be some slight differences in what we're doing. So let's go ahead and parse out the problem. I'm going to work through this. I'll pause for questions, but I'm going to go through the process relatively quickly, just being cognizant again of this very short, precious time we have together. So I'm just going to write for population 1, is it students? Let me see here, students. Students who take a 10-minute social media break. Students who take a 10-minute walk outside. And students, forgive my typo, students who take a 10-minute quiet rest. Our dependent variable is test. I'm just going to write test scores. Of course, if I was writing my study, I would specify what the test was. You'll notice I'm not asking you for tails because it's always one-tailed high. And we're just going to write for the research hypothesis, scores will differ significantly across groups. And I can just copy and paste this. By the way, when you're writing your conclusion, sometimes you can just copy and paste this, Cassandra, and then just replace the ambiguous information with specifics. So we'll just add our word not here, and these will be our hypotheses. We describe the comparison distribution as the F distribution and then we specify our degrees of freedom. So let's see if we can, let's actually go ahead and get that figured out by filling in some data over here. So over under, let me see here. This is actually set up a little, I have to change these conditions. This is actually set up for your application problem. Condition 1 is the social media. Condition 2 is the walk. Oops. Oh, there it is. Condition 2 is the walk outside. And condition 3 is the quiet rest. And we don't have a condition 4, so I'm actually going to just take this whole set here. I'm highlighting up in the numbers and I'm going to click delete. You don't have to, you can just leave it there. It's not going to hurt a thing. Okay, so let's go ahead then and fill in some numbers. I see that our N for number 1 is 9. Our degree of freedom, you might wonder why I do this, but I do this N minus 1 so that if I have a different problem, it automatically calculates degrees of freedom and saves time. And we know that M is listed for this group. It's 90.5. And we also have listed EVAR, which is 54.3 for this condition 1 group. I'm going to just paste that formula in. That way I don't have to do anything extra. Our N for condition 2 is 11. Our mean is 107.8. And the EVAR is 49.2. And in our last condition, our N is stated in the problem as 10. I have it set up to calculate DF automatically. Our M, mean, is 99.4, and our EVAR is 49.2. So now we can figure out what our degrees of freedom are. Let's go ahead and sum these up down here. If you go down a little bit, you'll see where it says find within groups variance. Let's get our DF total there. I'm just going to write equals sum, and I'm going to just go right across this row and select those, and it tells us our DF total is 27. And we already know our DF between. Let's label this the DF within. I think that's a better way to label it now. And we also know that our DF between is just the number of groups minus 2. We have 3 groups, so this is going to be 2. So those are the degrees of freedom that we'll be using to find out what our F distribution is going to look like. So we'll put the F distribution with 2. We always list the between groups first, and 27 degrees of freedom. And if that looks like a period, it's not. It should just be a comma, 2 and 27 degrees of freedom. I'll give you a moment in case you need to get caught up. Let's go ahead and find the cutoff point. As I mentioned earlier, I'm not requiring you to draw this anymore because it's just looking to see if our sample score is higher than the cutoff point. And do you need me to send you the link to the calculator tool? I will do that just in case, just to make it a little quicker for you. I'm putting it into the chat right now. And you can see now that calculator tool in the chat. And so let's see if we can find where it is. Once you have it open, you'll want to select the F value. Always adds. And our significance level is 0.05. We don't have to divide anything here for this omnibus test. Our numerator degrees of freedom, that's degrees of freedom 1 or degrees of freedom between, that's our groups minus 1. And our denominator degrees of freedom, that's our DF total or our DF within, and that was 27 according to what we calculated. We can hit calculate and learn that our cutoff point is going to be 3.35. I think that I'm going to draw it out just to show you what this looks like, again, since you're new to it, but I am not requiring you to do that drawing in your paper anymore. Just a second here while I get my pen on board. So our distribution is looking like this. It's a long, skinny one. We have 0 real close to that y-axis, and the numbers are going up something like this. It might help you to draw this on a piece of paper. And numbers here can really get, quite big. You can have, numbers 30. I mean, you can get really big numbers here in this ratio. We've discovered that our cutoff point, let me draw the distribution here, If you're drawing it in general, you're just going to draw it something like this. And we can see that our cutoff point that we just found was 3.89. Now I have to just double check that because I didn't write it down. It was 3.3541. I'll write F alpha equals 3.3541. And let's go ahead and draw that on that little distribution. I can see that 3.35 is going to be right around here. F alpha equals 3.35. And we're looking for a ratio that exceeds that. If you are drawing in your chart and your draw menu is gray like this, you probably just need to click in a cell and then your draw menu will show up visibly. We can then just shade in this region as our reject region. And here is our fail region right there. So you can do that or not as you please if you find it helpful. Our next is to calculate the F ratio. And so we need to have MS within and MS between, and then we divide the between by the within. It's actually, they're placed in reverse order here. And then we'll have our F observed, which is another way of saying our F sample. Now with unequal means, if we had equal means, we would just take the average of these. But because our means are unequal, we're going to weight them. And the weight that we're going to apply is the same as what we were naming proportion in the independent samples t-test. It's exactly the same. This time we're just calling it weight. So I'm going to write down weight equals what we called proportion earlier. And it's just df1 divided by df total or df within. So let's go ahead and calculate weight for each of these. I'll put my equal sign here and I'll click in the df1 weight and divide by the df within. We should get a fraction, 0.29, almost 30%. That looks about right to me. Let's go ahead and calculate our weights for the other two conditions. df2 divided by df within, and dft 3 divided by df within. Now we have each of these weighted, and so instead of doing a straight average, we're going to weight out our variances according to these proportions. You can see I have written here E var W1, which just means E var weighted. So E var W equals weight, I'm going to write small here, weight times E var. And that's it. You put a parenthesis around that. So let's go ahead and take our weight, this 29%. 29% of our degrees of freedom are here. Let's multiply it times E var. We find that now the estimated, we're going to use that 16. Let's take this weighted variance equals weight times E var 2. And let's get our weight for E var 3. Can you let me know if you're caught up with me or if I'm zooming ahead too quickly?
It's okay.
Okay. Cassandra, are you in there with me?
Yeah, I was changing my spreadsheet, so I kind of got behind, but then I caught back
You
up.
know all this stuff. You're good. Okay. So now all we have to do is sum those up. So MS within, that just means mean squares within. It's another way of stating E var. MS within equals the sum of all of the EVAR weighted. That's it. Equals the sum of all of these EVARs. You can just actually select these and run across that column, even though there's some words in the middle. And now we find out that we're going to be having 50 for our MS with it. We would expect it to be somewhere in the range of these EVARs, and it is. So it looks like the number is correct. So now we're done finding our within groups variance. That's what we're going to compare our variance between the groups with. So continuing on then, in this next box, we're going to calculate our between groups variance. You can see this is set up for 4 groups. We only have 3, so we won't be using this M4. You can delete it or leave it. It doesn't matter because we're not going to use it. So in order to get these means in place, I'm just going to reference those cells. I'm just going to type equals mean 1. I'm not going to type them in because I might make a mistake. Equals M2 and equals M3. Now we have our means in there. Let's make sure and put in our number of groups, 3 and 2 degrees of freedom for our DF groups. We already wrote that here, DF between or DF groups. Maybe I'll write DF between here just to be, these are all the kinds of things that are taking me a long time in getting this content prepared. Our grand mean is just the average of those other means. So GM is just the sum of all the means divided by the number of groups. The average, in other words. So let's just type average, say it like it is, equals the average of these 3 means. Now we're going to go through and just do a regular old calculation of, you can see this is deviation and this is squared deviation. Let's go ahead and do that. Equals each mean minus the grand mean. I'm going to put that $sign in there so I can copy paste. And now if this formula looks good, I'll check it, make sure I didn't mess up. The formula looks good to me. The $sign is there. So I can go ahead and just use this magic button and double click on it. Don't do it that way. Just double click on it. Just drag it down to these 3 means. That's our deviation. That's how far each mean is from the grand mean. We can square these. So what we're doing is we're calculating a sum of squares. We can copy that formula down also. And there's one more step that's a little bit different here that we're going to be doing at the very end here. So first off, this is our sum of squares, but we're not actually going to be using it much because what we're going to do first is multiply by n. So we're going to go equals, and let's take for each mean, let's get and multiply by n. For mean 2, I'm going to click on the squared deviation and multiply times the number of in that sample. And for the third one, I'm going to take the squared deviation and multiply by the number in the sample. Now we're going to take our sum of squares is actually going to represent this column right here, the sum of squares times n. So let's go ahead and get our sum of that last column. And now we divide that by our degrees of freedom. Okay. So it's a slightly different process, and this is the one that I'll invite you to do consistently so that you don't have inconsistency when the means are equal and not equal. So I'm going to change this SS between to just write, let's see, it's SS times N because we're actually using that very last column instead of the straight up SS column. So let's like SS times N. And I want to make a comment about the upper and lowercase n. The reason we use a lowercase n now is because we're referring to the number in each group rather than the number overall in the sample, and we use a lowercase n for that. So in case you got behind on that, we took the means from above, we subtracted the grand mean, we squared them, and then we multiplied those squares times the number in the sample. That's what we summed here to get the sum of squares times n, and we divided by degrees of freedom to get ms between. So I'll write that formula here, ms between equals SS, I'm just going to put this little I here, meaning we do it for each group, times n for each group, and we divide by df between. Times, I'm not sure if that's clearly indicated. Could just put it with the pairs of parentheses here. That might be a better way to show it. Questions about that last little maneuver we just did?
No.
Okay. Then let's calculate our F ratio. We're done. Here's our MS. We're done with that at least. Here's our MS between. So I'm just going to reference the cell so my numbers are right in front of me. My MS within, I'm just going to reference that cell too. And to get the ratio, the F observed ratio, I'll just write F observed to distinguish it from F alpha. We take MS between over MS within. And if you think you might forget which is which, just remember, keep them in alphabetical order. The MS between is on top because it comes first in the alphabet. The MS within is on the bottom. It comes second in the alphabet. That might help you to remember. So let's get our ratio equals MS between divided by MS within. We have our F score of 8.05. If we scroll down and mark that on this chart, remember I said these large F scores are definitely possible. It's going to be somewhere out here. I'll write F observed equals 8.0. I can't remember what it was now, 0, 1, 0, 9, 0, 5. 8.05. It is definitely in the reject region. I highlighted these just so you can remember you are just comparing what we just calculated with the F alpha, which is 3.89. If our F observed is bigger, we're rejecting the null hypothesis. So let's go over here and write down our F observed. I think I'll just reference it. So now we are ready to decide and conclude. Our decision has to be to reject HO. And we will just conclude that, let me remember what our problem is here, that test scores differ significantly across was it study conditions? Let me see. Across three break conditions. And that's all we can conclude from that. We can write our statistic. I'll go to a new line and put our F statistic. We put our F statistic, and in parentheses, we write our two figures, always starting with the between groups. We had 2 and 27 for our degrees of freedom. The F score was 8.05. You only need 2 decimal places. That's all you should put. And the probability we tested at was 0.05. Now, if anyone just read this result, they would be saying, okay, but I have no idea which group is different. What should I do? Should I take a 10-minute break? Should I rest? Should I walk? Should I go on my phone? Which one is going to be significantly different? And that's where we have to go into our planned contrasts. I have these set up for you to do below. And I've asked you in this first case, I didn't tell you exactly what the contrasts are. Instead, I wrote it into this sentence. She hypothesized that students taking the social media break would perform worse than those who walked outside or those who rested quietly. So I can see that I'm going to compare the social media break, which is group 1. I'm going to compare it with the walk outside group, which is group 2. And I'm going to compare the social media break group with the quiet rest group, which is right here. So let's go ahead and do it. I'm comparing group 1 with group 2 and group 1 with group 3. I have 2 contrasts, so I'll have to divide alpha by 2. So this is where we're going to work these 2 planned contrasts. Planned contrast 1 is going to be group 1, our social media, versus group 2, our walk outside group. And then next, we're going to do group 1, our social media group, versus group 3, our quiet rest group. So these are the planned comparisons that we're asked to do. We can figure out right away a few things. We know that we just have 2 groups now, so we put 2 there, and our degree of freedom is going to be 1 in terms of the number of groups. We'll get DF total in a moment. Let's go ahead. Well, actually, we should get it right away. DF total is just the sum of the degrees of freedoms for those 2 groups. I'll write it down here. DF total equals the sum of DF1, and in this case, DF2. And so let's go ahead and get our DF total equals sum. And I'm going to just scroll up and click on the relevant cells. There's for DF1, adding a comma, and selecting the cell for DF2, hitting enter. We can see our DF total will be 18. Our means have already been calculated, so let's just go ahead, just like we did here. This is the same process we're using. Let's grab those means once again. I can just grab them from right here. There's mean 1. And the walking group, condition 2, what we're comparing here. Let's type the equals and just grab the mean for condition 2. We next figure out our grand mean, which in this case is the average of mean 1 and mean 2. And now we're going to calculate our, I wrote it again this way. Let's write our sum of squares times n. And so we'll go ahead and get our deviations. We take each score and subtract the grand mean. And so that I can use copy paste, I'm going to put the $sign there. And we'll find out that this is going to be exactly the same. It's always going to look like this. Minus 8.65 and 8.65, representing that each of these should be equally far from the grand mean. If it doesn't look like this, you made a mistake. These, when you only have two comparisons, should be equal with one of them having the minus sign. We can square our deviations. And now we just multiply times the n for each group. Might have been nice if we had put these n's in down here, but we didn't. So let's go ahead and get them. Equals the squared deviation times the small n for each group, which I'll go up and grab from here. And let's do that again for this one. It should be the same thing. I mean, it's not necessarily the same thing because we're multiplying it by a difference n, actually. If the groups were equal, it would be the same. So this is the column that we sum to get our SS between. Equals the sum of this last column. And then we divide that by DF, by this DF total right here, in order to figure out our MS between. So we're going to take this number, this SS, and divide by DF. And I'm talking about this DF total here. Now, I'm going to jump this square for the moment and go right down to get our F statistic for this planned contrast. And we get this F statistic. I'm going to write this down here. Our F observed is just equal to our MS between, this S should be big, divided by that old MS within that we calculated earlier. So let's get our F statistic equals MS between divided by, and let's go way back up there and find that MS within statistic from earlier. And we find that our F observed is 1.64. Let's find out what our cutoff point is, but we need to do this Bonferini correction, which just means we divide alpha by the number of tests. We are doing two tests, this one and this one. So we take alpha and divide by 2. Equals 0.05 divided by 2. Now we can use this information. We're going to use degrees of freedom 1 and 18 to find out what the cut point is for alpha of 0.025. So let's get our tool up. We have to enter significance of 0.025. Our numerator is just 1 now, and our denominator is 18. When we calculate, we learn that our cutoff point is 5.9781. If we were to draw that on the chart, I should have copied it, 5.9781. In order to reject the null, we need our observed score to be higher than alpha. So what should our decision be in this case? If we were to imagine it on this chart, what should our decision be?
Fail.
We're going to fail to reject HO. And so our first planned contrast did not yield a significant result. We don't have to write any conclusion there because we're going to write that statement up here. That's what this little hint is doing for you. Let's do our one more planned contrast. We can preserve some information from over here. First off, we know that we have our mean for group 1 handily right here. So let's put that there. And our mean for group 3, let's go up and grab it. Here it is right here. I'll just take it from right here. We can get our number of groups is still 2 and 1. And let's get our DF total. I think, let's see. I wish I had those ends written into this. As I'm creating these documents, I realize things I could have done better. So let's sum up our degrees of freedom for group 1 and group 3. Going up to here, here's our degree of freedom for group 1, putting a comma and selecting the degree of freedom for group 3. And we have now 17 degrees of freedom. And let's calculate our grand mean. Equals the sum I'm going to use the average function, equals the average. Am I having typos there or not? And then we'll select these two. Next, we're going to calculate this deviation, equals our mean minus the grand mean. We can put our $sign in there in order to allow the copy paste. And let's square these. And let's multiply times n. We'll multiply this one times the n for 1, which is up here. And we'll multiply the second one, selecting this sum of this squared deviation, and multiplying it times the n for group 3, which is up here. Then we can sum those, and once again, I'm going to clarify that. It's not quite the sum of squares anymore. We're going to sum up that column. And divide by degrees of freedom. Okay. And I made a mistake. I kept looking at it thinking I was making a mistake. That's because I'm new to teaching it. I'll show you what the mistake was, and then we'll correct it in our first contrast. So let's go ahead and calculate MS between, not by dividing by the DF total, but by the DF groups. And I apologize for that mistake here. So we have our DF total written here, but we're actually just dividing by the number of groups, which is always going to be 1, and so there's no change. And I just had a little brain mess up there. We're going to divide by the number, the degrees of freedom for groups, which is 1. We'll end up with the same number. Our F ratio should have been significant, and that's why I kept hesitating, wondering what did I just mess up here? So let's go ahead and this is what our MS between is. It's actually just going to be the same as this number. And so let's just go ahead and do that. Technically, we are taking this number and dividing by degrees of freedom groups, which is the 1, and so it's going to be the same. And now we can see that our F observed is quite high. I thought that was significant, and in finding that it wasn't, I knew that I had done something wrong there, so I apologize. We're dividing by the number of groups. This allows us to reject the null. Let's see what our F ratio is in this case. We know that our Bonferroni corrected alpha is still going to be 0.025, and our F observed is now going to be equals our MS between divided by that MS within, same number as up here, and we find that we have a 7.419. In this case, let's look up our cutoff point. This looks like it's going to be really close. So let's go ahead and look up the cutoff for one group, 17 in our second DF, and let's find out our 0.025 cutoff point. So here's our 0.025, here's our 1. Let's change to 17 and calculate. And we find that our right-tailed critical value is 6.042. 6.042, and that allows us, we can see that our number in our observed is bigger than our number in the F alpha, and so that does allow us also to reject the null hypothesis. And so now we have found significant differences between those two groups, and this is the important piece to write in our concluding statements. So we'll remember these two F ratios. And let's go ahead and I'll show you how this is done if you want to do it absolutely perfectly. We could write planned contrasts between, let me see what we're testing at again, individuals who had a social media break and those who walked outside. Planned differences between students who took a social media break and those who walked outside. Let me just see if I want to state it this way. I think I want to be even more specific. Planned contrasts, I'm going to say showed that students who took a social media break, and let's look at what their test scores were. I can see that the social media break was lower, so let's put that social media break had significantly lower test scores. And now I would put the mean there. Mean equals 90.5. You guys are just going to do your best with this, okay? Then those who walked outside. And now we would want to probably put another mean score for them. And their mean was equal to 107.8. And here, right here in the middle of the sentence, we're just going to put our F score. Our F, and let's put our 118 equals, and it was 29.51. I'm going to put it in the negative range because we have a lower result. And now I'm just going to finish the sentence. I'm referring in my sentence to the students who took a social media break. And I wrote, students who took a social media break had significantly lower test scores than those who walked outside and those who took a quiet rest. And in parentheses, I'll put the mean for that group, 99.4. And then I'll put that F test result, F 1 and 17. What was that F test? It was 7.42. And I can put the P, I should have put the P less than 0.05. And here I should have put the P less than 0.0, probably P less than 0.01, but we'll just write.
Shouldn't that be 29.51?
Yeah, what did I write?
21.
29.51. So this is this is what you'll see in a research article. We've informed our readers of a lot of things. We first informed them that we had an omnibus difference, that we did find that these groups weren't the same. That was our first sentence. Then we described to them that we had planned in advance. We had these planned contrasts. And I listed p less than 0.05, but we tested at 0.025. Then we told them the means for each of these groups and how they compared, and that they were both significant. If one of them had not been significant, we would finish the sentences by writing, but not significantly lower than those who took a quiet rest. But in this case, they were both significant, so this is how we would write that. It's kind of a long, confusing thing, but this is how we would indicate all of that.
Does the second p-value have to be 0.025 as well?
Yes, it does. Boy, Cassandra, if I could hire someone with your eyes to be a teaching assistant, I would be so grateful.
Also, can you explain why you did the negative for the negative 29?
Yes. Yeah, because it doesn't matter which way we subtract these.
Okay.
In this case, I was stating, so it would be the same if we subtracted the other way around. Let's imagine that we did for our, let's see here. Let's imagine that we did these instead of subtracting I-36 minus K-42, we did it the opposite. Let me see here. Actually, let me see here why I said that negative. It's correct, but let me see if I can explain it. Let me say it this way. If I had stated it the opposite, if I had said those who walked outside had higher test scores, and no, I can't explain it. That's what I would have done in a t-test, but this is not. This is just the ratio. So no, this should have been a positive number, 29.51. So that was an error. This is why it's taking me so long to prep things out. So I just haven't had enough practice explaining everything. It is not possible to get an F ratio that is a negative number. We're always using that skewed positive distribution. That was my mistake. My mind was going to the independent sample t, where we would reverse the sign of the t-score, but that's not true for the F score. So thank you again for your good eyes pointing